In 2014, a Hollywood film got a phone call from a Nobel Prize-winning physicist. Not to consult, not to advise. To tell them they had accidentally discovered something real. The simulation team at Double Negative Visual Effects built a black hole for a movie. A fake one. A pretty one for the cinema. What came out the other end was a peer-reviewed paper in the journal Classical and Quantum Gravity. They had rendered gravitational lensing around a Kerr black hole with such precision they had produced new science. By accident. But here's what nobody talks about. The ending, the Tesseract, the bookshelf, the fifth dimension. Christopher Nolan said it was theoretical. Kip Thorne said it was speculative. So which parts are real? And how close did they actually get? Strap in. Because the answer is more terrifying and more beautiful than the movie ever let on. First, let's talk about what Cooper actually falls into. Gargantua is a Kerr black hole. A rotating black hole. And that distinction matters more than almost anything else in modern physics. A non-rotating Schwarzschild black hole is brutal and simple. You cross the event horizon. Space-time tilts. Every direction, even forward in time, now points toward the singularity. You die. Physics ends. Curtains. But a Kerr black hole? A spinning one? It has two event horizons. The outer horizon is where light can no longer escape. Standard stuff. But inside that, between the outer and inner horizons, physics gets weird in a way that Schwarzschild black holes simply don't allow. In this region, called the Cauchy horizon, the singularity stops being a wall in space. It becomes a wall in time. Think about what that means. When you fall toward a normal singularity, it's ahead of you. It's a place. But inside a Kerr black hole, the singularity is in your future. And the ring-shaped singularity at the center might, according to Einstein's equations, allow passage through it without being destroyed. I said might. Hold on to that word. You're going to need it. Now the film's most iconic claim. Time dilation on Miller's planet. 1 hour equals 7 years on Earth. Is that real? Yes. Embarrassingly, yes. Gravitational time dilation is not science fiction. It runs on every GPS satellite right now. The onboard clocks tick faster than clocks on Earth because they're in a weaker gravitational field, and engineers correct for this deviation every single day. Without the correction, GPS would drift by roughly 10 kilometers per day. The math for Miller's planet checks out. Kip Thorne calculated that to achieve a 7-year to 1 hour ratio, the planet would need to orbit Gargantua at about 1.001 times the radius of the innermost stable circular orbit. The margin is razor thin. Any closer and tidal forces would shred the planet apart. Any further and the time dilation ratio drops off dramatically. The movie threaded a needle. And they knew it. So here's your halfway answer. The short version. The comfortable version. Interstellar got the black hole visuals right. It got time dilation right. It got gravitational waves, frame dragging, and relativistic orbital mechanics, surprisingly, remarkably right. The consensus was that Nolan and Thorne made a beautifully accurate hard sci-fi film dressed up in Hollywood clothes. A satisfying answer. A clean ending. Science wins. Except the Tesseract. That's the part nobody has been able to fully defend. In the film's climax, Cooper doesn't die inside the black hole. He's pulled into a 5-dimensional construct built by future humans, where he can navigate time as a physical dimension and interact with the past through gravitational signals. Kip Thorne, the Nobel laureate, the man who wrote the physics Bible for this film, called this part speculation on top of speculation. So what's the actual science underneath that speculation? Here is where it gets genuinely strange. The theoretical foundation for the Tesseract comes from something called the bulk. In the film, the bulk refers to a higher dimensional space, borrowed directly from string theory and M theory, in which our entire universe is a 3-dimensional membrane, a brain floating in a larger dimensional structure. This is not a movie invention. This is a real theoretical framework being actively researched by real physicists. The Randall-Sundrum models, developed by Lisa Randall and Randall-Sundrum in 1999, proposed that extra dimensions could be large and accessible, with gravity leaking between branes. These models are testable. Some versions of them make predictions about what we detect at particle colliders. We haven't detected them, but we haven't ruled them out. Now, here's the piece that stops physicists cold. The film's premise requires that gravity can operate across dimensional boundaries, while light and matter cannot. Cooper's gravitational messages to Murph. And bizarrely, that's the correct prediction from the Randall-Sundrum framework. Gravity is the one fundamental force that, in some higher dimensional models, is allowed to propagate through the bulk. It's why, in our universe, gravity is so dramatically weaker than the other forces. It may be spreading itself across extra dimensions we can't directly observe. The movie accidentally stumbled into the one force that might actually work this way. But here's where the real physics hits a hard wall. Navigating inside a black hole as a fifth-dimensional structure and transmitting meaningful information back through a closed time-like curve to your own past. This requires what physicists call a stable traversable structure inside the event horizon. And right now, the physics there is genuinely unsettled. Not we think it's unlikely. Genuinely unsettled. The Cauchy horizon inside a Kerr black hole, the mathematical boundary where time becomes navigable, was long assumed to be unstable. The mass inflation instability suggests that any perturbation, any stray photon, any gravitational wave crossing the horizon would blue shift to infinite energy and destroy it. But in 2018, new theoretical work from Mihalis Dafamos and Jonathan Luke at Princeton and Cambridge suggested something uncomfortable. The Cauchy horizon might not be as unstable as we thought. It might be singular, but it might be a weak singularity. One that's mathematically pathological, but physically survivable. The universe may have left a door open. A very dangerous, very uncertain, very real door. Here is the thing about Interstellar's ending that nobody says out loud. It is not a story about a man going into a black hole and surviving because of love. It is a story about a species, our species, that someday, in a universe with 5 dimensions and a bulk and leaking gravity and rotating black holes with survivable Cauchy horizons, might just barely find a way to reach back through the fabric of space-time and hand itself a second chance. That is not sentimental. That is the coldest, most rigorous version of hope that physics currently permits. The real question that Kip Thorne leaves open, the one he wrote in his companion book, the one he won't fully answer, is whether an infinitely advanced civilization could engineer the bulk, could stabilize the structures inside a Kerr black hole, could transmit information across dimensional boundaries. His answer, characteristically precise, was this: the laws of physics do not forbid it. Not it's possible. Not it will happen. Simply, the laws of physics do not forbid it. That is the most terrifying and the most beautiful sentence in modern theoretical physics. Because it means that right now, at this exact moment, inside every rotating black hole in the observable universe, an unknown number of things are happening that our mathematics can describe, but our minds cannot hold. And somewhere in that darkness, the door might still be open. We just don't know what's on the other side.